Hello everyone, here's our video abstract for a recent publication in Journal of Chemical Education titled Identifying Generative Artificial Intelligence Chatbot Use on Multiple Choice General Chemistry Exams Using Rasch Analysis. But before diving into the details of the paper, just thought we'd give you a little bit of context on this. And so in fall of 2017, we started an endeavor where we're using Rasch analysis, these statistical tools, to improve exam and question quality over the course of 3 semesters. And we saw, yes, the exams got better, and you can check out the paper in Journal of Chem Ed in 2021. There's the reference right there. But then something interesting happened, which was COVID. And so what COVID did is forced us online in fall of 2020. And so both the lecture and the exams were online. And we decided to do an additional study where we looked at, is there a difference between in-person and online exam outcomes? And interestingly, you can find in this paper right here, the 2023 paper, we found that generally student outcomes were very similar. There was no increased prevalence of cheating, at least as far as we could tell when comparing the in-person versus the online classes. But something interesting happened during the reviews of this particular paper, and it was someone brought to our attention, like, yeah, there's a less prevalence of cheating during this time window, but they brought up the point that ChatGPT was introduced basically at the end of fall of 2022, and the question was, would ChatGPT usage change these outcomes? And so it really inspired us to look at this and say, what would ChatGPT look like on a multiple choice exam? And so what we did is we took, those 5 semesters worth of data, but we started with spring 2019 exam 1, just the first exam of the semester, and we fed every single question into ChatGPT 3.5. We used 3.5 specifically because it was free and ready to use, and so we fed every single question in and we recorded the response. And so for this first exam, we recorded the response 20 times, and we got, average performance per question, as well as the answers for each individual question. And so we did this for a bunch of different tests, particularly this is the spring 2019 General Chemistry 2 exam outcomes. And you can see for all questions, ChatGPT performed a little bit lower than the students. And this is one of the reasons is it can't process images. So any question that had a figure, obviously ChatGPT would not perform well. But even if you look at the text-only questions, ChatGPT was on par or slightly below student performance. And so based on these raw numbers alone, we said, okay, we cannot distinguish ChatGPT from a student or a low-performing student. And so they look, for the most part, the same. And so we decided to dig a little deeper using something called Rasch analysis. And so here's the equation right here. This is part of modern testing theory that basically says there's a relationship between student ability and question difficulty, student ability being theta, question difficulty being beta, and the probability of success on any given question is related to these 2 variables. And graphically, it looks something like this, where on the x-axis we have student ability, on the y-axis we have probabilities of success. And so for any given question, we'll say it's an average difficulty question. An average student will have a 50% success rate, a high-performing student will have a higher success rate, and a low-performing student will have a lower success rate. And so this Rasch modeling basically allows us to fit all the questions and all the students and compare their ability versus question difficulty. And we get a graph that looks like this, also known as a right plot. And so in these graphs, we have student ability in blue here, and then question difficulty in purple here. And so you can see how the student ability and question difficulty align. This is for all questions, and then here's for the text-only questions. And so fitting the ChatGPT outcomes, we see they're in this gray region here. So below average student ability on all questions, near average student ability on text-only questions, which is similar to what we saw in the raw percentages. And so that alone didn't give us any insights into ChatGPT having some kind of unique behavior. But when we started to look at the per question outcomes, there were some striking differences between students and ChatGPT. And despite ChatGPT being average student, it didn't answer the same questions correctly or incorrectly. And so here you can see an example where on question 1, student success rate was 36%, ChatGPT was 100%. Alternatively, question 2, students were 74%, ChatGPT got it wrong every single time. And so the per student or per question success rates vary dramatically between students and ChatGPT. And so we asked the question, can we use this fitting to the model to detect ChatGPT usage? And so the idea behind this was, students generally follow this behavioral pattern. Hard questions are hard, easy questions are easy. But ChatGPT doesn't answer like a student. And so you can imagine ChatGPT outcomes being, high or low. Like they have a 100% success rate on an average question or 0% success rate. The point is that they're outliers or outfits on this particular model. And so what we did is we used this fitting statistic and we amplified it through this process. I won't go through the details, but basically we take the text-only responses, look at the questions where ChatGPT did really well, fit it with Rasch modeling, fix that ability, fit it again for all questions, and then we looked at displacement, which is the change in ability, and the outfit statistic, and then set a detection threshold. And so you can read about these details in the paper. The point is we're amplifying the magnitude of the outfit statistics. And so in this case, we use the Z standardized outfit statistic. And so there you can look at the actual description of what this fitting statistic is. But it's basically looking at how far outside of the normal probability student ability relationship it is. And so students lie somewhere on this line. ChatGPT gave us high outfit statistics because it was an outlier in fitting with this given model. And so we can actually graph this outfit statistic and frequency. And so you can see here students, for the most part, which are in blue, they give a normal distribution with a few high outliers and a few low outliers here. But you can see ChatGPT consistently had a very high outfit statistic. And so you can see it over here. All the ChatGPT outcomes are distributed away from the student to at least the normal distribution. And so if you set a detection threshold where we detect all the ChatGPT instances, this basically says only 5 out of 235 students look like a ChatGPT-like outfit statistic. And so this, if we use this as the raw threshold, this gave us a false positive rate of 2.1%, which isn't bad. It's basically saying ChatGPT is behaving very differently than students. And so we did this over and over for every single exam across 5 different semesters, 4 exams, 3 midterms, plus a final. And you can see nearly across the board, ChatGPT, the red outcomes, are consistently outliers on the high end of the Z-out statistic. And so you can see it on almost every one of these. And so just looking at some of these, if we set a true positive rate of 1.0, that's basically saying 100% detection for ChatGPT. We can see the false positive rate is below 10% on all of them, and a few of them are actually less than 1%, which is a remarkable detection. What's not obvious to us is why it's better at detecting on some exams than others. Our assumption is there are certain instances where ChatGPT and students had similar high success questions, and in that case, the fitting algorithm we did biased it towards ChatGPT looking like a student. But that's something we're looking into the future. But regardless of this, some of them not being as good as others, generally this is a pretty good detection strategy. But obviously it's not a perfect detection system. And you can see in all these instances, some students end up looking like ChatGPT in the outfit statistic. And so with any detection strategy, you have to do this balance between true positive rate and false positive rate. And so one way to do this is using a receiver operating characteristic curve, or ROC plot. And it's basically this graph of false positive rate versus true positive rate. And so the idea behind this is you start at a really high detection threshold where it doesn't detect false positives, or its false positive and true positive rate is very low. And then you basically decrease the detection threshold. So you're just iteratively decreasing the detection threshold, saying how many true positives do I get? How many false positives do I get? And you end up getting a curve that looks like this, or a ROC curve. And so the outcomes of this ROC curve, it's basically a way to generalize how good of a detection system is this, not at any specific threshold, but basically at all thresholds. And so a random classifier that does a 50-50 guess between, being ChatGPT or being a student would give you this diagonal right here, would give you this line. The better it gets at detecting, the more the curve will end up like this. And a perfect classifier will be basically a right angle here, where it's 100% true positive rate, 0% false positive rate. And so you want these ROC curves to look more like the blue than you want it to look like the orange or red. And so the way to quantify this on these ROC curves is the area under the curve. And so for a random classifier, something that's not working at all, area under the curve is something like 0.5, right? It's this diagonal, and the area under the curve is half the total area. You get a 0.5. A perfect classifier would give you 1.0 because it's this perfect right angle. That's the area under the curve. And so there's some generally accepted ROC statistics, or area under the curve statistics, where if it's 0.5, it's random response. Less than 0.7, it's unacceptable. 0.7 to 0.8 is acceptable. 0.8 to 0.9 is excellent. Greater than 0.9 is outstanding. And so obviously you want to have this area under the curve as large as possible, and that tells you how good your detection system is. And so generally anything above 0.8 you're excited about. Anything above 0.9 is outstanding. And so we generated these ROC curves and got the area under the curve for our comparing ChatGPT and student outcomes. And you can see if we use even only 2 instances, basically we feed questions into ChatGPT twice, and that's how we use to fit the model. Even that gives us a area under the curve greater than 0.9. And you can see as we use more and more instances of ChatGPT, we're better and better at detecting that type of behavior. But you can see in all cases, these are outstanding outcomes, even using n equals 2 data sets up to n equals 6. And so consistently across almost all the exams, we got area under the curves that were outstanding. 18 of 20 of them were greater than 0.9, and 20 of the 20 were greater than 0.85. So in the excellent range, approaching the outstanding range. And so what this basically tells us is this method of trying to detect ChatGPT is actually really good at doing it. You get a few false positives, but depending where you put that detection threshold, you can differentiate ChatGPT from student performance with a pretty high degree of confidence. And so major conclusions from this paper: average score and raw fit statistics were insufficient to identify ChatGPT-like behavior. If you're looking at the raw score, ChatGPT doesn't look that different than an average student, but we can use this Rasch analysis and fixability to amplify the differences in outfit statistics between the two. And with that, we got relatively low false positive rates, even when the true positive rate was set to 100%, and we got excellent or outstanding ROC area under the curves for all the exams. And so it basically says this is a really good method to detect ChatGPT, at least in a statistical sense. But we do leave the conclusion with a bunch of limitations or qualifiers on why this works or why it might not work. And so one of the concerns is if a sufficient number of the students use ChatGPT answers, then the student response and ChatGPT response end up looking the same, right? And so if half the class ends up using ChatGPT to cheat, then it would be really hard to distinguish the two. And so it's going to be harder to detect. As generative AI improves, it'll become more difficult to detect. Basically, as it gets better and better at answering, it's going to be impossible to distinguish high-performing students from high-performing ChatGPT. And so as ChatGPT or generative AI gets better, it's going to be more and more difficult to detect. And that's just an arms race in the technology versus the test writing quality. The other thing to note is no statistical tool alone is capable of confirming cheating. As we showed in these results, there were false positives that said a student looks like ChatGPT. But all this analysis, all these tests were taken by the students before ChatGPT existed. And so they are false positives. The students did not use ChatGPT, but sometimes they look like it. Sometimes they got hard questions right and easy questions wrong, and they had the similar outfit statistics. And so you'd have to do something more rigorous, like looking at, similarity analysis of the negative outcomes. But nonetheless, the closing sentence of our paper is, regardless of these limitations, and while analysis reported here is by no means exhaustive, the goal with this work is to propose an avenue of pursuit and inspire discussion on possible means of detecting generative artificial intelligence chatbot usage on multiple choice exams. As far as we know, this is the first report to try to look at ChatGPT or any generative AI on multiple choice exams, and the results are promising. They're not absolutely perfect, but they are getting in the right direction in terms of detecting ChatGPT. With that said, would I encourage the average professor to do this on single exams? Probably not. This might be worth doing on standardized exams where thousands of students are taking it, but not necessarily on an individual per classroom basis. But it is promising nonetheless. And so a few acknowledgements: Florida State University for letting me do this research and approving it, allowing me to do it in my general chemistry classroom. Shout out to my longtime friend and collaborator, Benjamin Sorsen, who does the data analysis and the statistics behind these exams. Also, thanks to my teaching assistants between spring 19 and fall of 2022. They help write the exams as well as do recitation and answer students' questions. And so I really appreciate their help through this process.